Surds. So of all the irrational numbers we look at, we probably see surds more than any other irrational number. What is a surd? It's any number that includes a radical symbol. That's a radical symbol. It doesn't have to be square root. It could be cube root, fourth root, fifth root. Any radical symbol is a surd. But the thing is, it cannot be calculated exactly. That's what makes it irrational. So something like the square root of 4 is not a surd, because you can calculate that. That's 2. You would simplify it down. Some rules, some laws that allow us to manipulate them. Let's briefly go over them. Remember, if we multiply them together, we can do it that way. So I guess with numbers it means you could find the square root first and then multiply, or you can multiply the numbers together then find the square root. But basically that's the idea that allows us to simplify surds. Division is also true. Find the individual square roots first, or do the division first, doesn't matter. Squaring and the square root are inverse operations. They cancel each other out. So the square root of a squared is a, and that's basically it. We can then manipulate surds to our heart's content. So we see the square root of 50, and the idea, of course, is we're trying to find a perfect square, and the biggest perfect square that goes into the number, which is, of course, 25. Not suggesting you would write this down, but the square root of 25 is 5, so we know that's 5 root 2. We talked about this the other day. But let's look at it again with algebra. Square root of x cubed, well technically that's the square root of x squared times the square root of x. Square root of x squared, it's sort of x root x. It's not really x root x actually. But we write it as x root x. I say the square root of x squared is not x. What is the square root of x squared? The absolute value of x. Because of course if x was a negative number, you would have to have the absolute value. Root 5 on 4, well the bottom of the fraction we can work that one out, the top we can't, so we leave it as root 5 on 2. 20 on 9, we can play with both of these, the top simplifies down, there's 2 root 5, the bottom is 3. I mean these are the idea behind the square roots. Okay, arithmetic. Get ready for your mind to be blown yet again. Now that's exactly the same as the first bit of theory we looked at this year. I've just changed one word. Before we had the word terms. Like terms can be added or subtracted, unlike terms cannot. I've changed it with surds. Why is it exactly the same? Well, because a surd is unknown. We don't know what it is exactly, and that's exactly what a pronumeral is. It's an unknown. It's something we have to find. So all these rules that we have for algebra pretty much apply to surds as well, and that's how we manipulate surds. So we get something like this, and we say, well, we can add and subtract like terms, and we pull it together, and we get 3 root 3 plus 8 root 2. We can't add the root 3 with the root 2 because we don't know what they are. Just the same as we can't add the x with the y. We don't know what they are. Binomial product. That's all it is, really. We've got 3 plus an unknown. So first outside, inside, last. There's my answer. Nothing there adds together, nothing there simplifies. Difference of 2 squares. In fact, this comes up a lot in our questions because what we've got there are what we call conjugate surds. The actual terms are the same, but one of the signs is different. And in this one, it's the 1 has a negative in one and plus in the other. Notice it's only one of the signs is different, makes them conjugates. Difference of 2 squares then, so we have root 2 squared minus 1, 1. Perfect squares. Again, first term squared minus twice the product plus the last term squared. This of course tidies up. 6 minus 4 root 2. So all of those algebra ideas we can keep using. Back to surds.